Hi, everyone, and thank you very much for the opportunity by Katie and EPoSS to present at the AI at the Edge Ability webinar. I'm very honored to be here today, my name is Hal. I'm a co-founder and CEO of RoboK, and I'm here to present on a topic very close to our heart, that is sensing at the edge, about optimizing AI-based computer vision solutions for low-power embedded systems. So for today's session, I will first start with an introduction on perception, the application of it, and the challenges associated with performance at the edge. And then I will give a few technology demonstrations showcasing examples of embedded intelligence at the edge, and also offer some case studies, including our collaboration with partners and customers, and also talk in general about AI-based perception going forward, about the trade-offs and the opportunities. So perception, it is really about understanding the environment. It is about understanding where you are, what is around you, and what they mean. It is an important building block for autonomous systems, and it can use sensors such as cameras to perceive and measure the environment. Other sensors could include radar, LiDAR, etc. Usually with AI-based software solutions, that could often require powerful computing platforms for real-time performance, and especially for those safety-critical applications. So for advanced perception, some of the application could include unmanned aerial vehicles, autonomous drones, autonomous vehicles, robotics, and as well as use cases in advanced manufacturing, specifically related to Industry 4.0. But the perception system is a combination of hardware and software. And for this kind of different applications, it could often require different level of accuracy and performance. And because there's a trade-off as well, that's on cost and performance, this is especially critical for achieving cost efficiency and competitiveness of the product and solution, especially for a wider adoption. Some of the challenges for at the edge could come within the selection of sensors. So if I take localization application as an example, which is a method and a process of understanding where it is locally and globally, if we look at different sensors, there's a different level of trade-off between cost of sensors, the computational complexity, and the accuracy it is able to achieve. And there's also the underlying advantages and limitation with each kind of sensors. For example, take camera as example, while it is able to provide rich information, it could be limited by lighting conditions, situations such as motion blur, or in textureless area that could all have a detrimental impact on the performance. So in essence, it's really about the trade-offs between the cost of the sensors and performance in trying to use AI-based perception for the specific application. In terms of the computational cost, I think during the sessions, we talk about using sensor fusion that utilizes multiple sensors and their respective strengths and advantages for more robust performance. But that would really mean even more data. With a multi-model sensor fusion approach, it could easily produce terabytes of data each hour. But as mentioned before, real-time processing is especially important for safety-critical applications. And those powerful powerful and complex AI algorithms often require a powerful computing platform, as shown in the picture here, where it is basically a trunk of GPUs in order for the autonomous vehicle to be able to make decisions in real time, robustly and safely. So what I'm really going to talk about is embedded intelligence at the edge. What optimization really means for AI-based perception, it is about design of the efficient deep neural networks and also applying optimization methods to inferencing, such as using quantization, pruning, and also looking at specific hardware architecture and accelerators. The optimization would mean a reduction in the size of the model and also a reduction in the latency. And that is about the amount of time to run an inference instance for a specific model. So instead of processing in the cloud or powerful processing units, it could mean deploying AI-based perception models on single board computers, as an example shown on the right, as an example of a multifunctional perception running at the edge. Let me give a brief introduction to RoboK. We focus on developing embedded intelligence at the edge. And that is about vision-based 3D reconstruction, optimized for low-power embedded systems, and also utilize the camera as the main sensor for optimized detection in both 2D and 3D, localization, tracking, and in particular, depth estimation from 2D images on low-power embedded systems. We are a spin out from the computer lab at Cambridge, and we have been working with customers and partners in applications such as in a digital twin for autonomous emergency braking and other advanced driving functionality, and also as 3D sensing modules for both passenger and commercial vehicles in both retrofit and also for the actual production programs. And also we work with partners in sensor fusion that's utilizing sensors such as cameras and IMU, also working on embedded systems for robust localization for indoor and outdoor applications. In terms of the technology that I'm about to demonstrate, it is about embedded intelligence at the edge. What it means, it's about creating robust 3D perception for low power computing platform. And the main sensor is about using monocular RGB camera that has the benefit of reducing the cost of the sensors and also, therefore, the cost of the systems. We've worked with both real-world data and simulation, and the key benefit and the key vision is about enabling scalable and cost-effective autonomous navigation solution for applications such as cars, robots, and machines cost-effectively. Here are some more demonstration of the vision-based sensing for low-power computing platform. And here on the left is about examples of extracting features for 3D reconstruction directly from 2D images. And on the right, it's a multifunctional model including detection, tracking, lane detection, etc. from 2D images or on embedded systems. We have recently presented our work on localization at the edge at the ARM Developer Summit and presented our discussion on how do we optimize a sensor fusion-based localization, specifically for low power embedded systems for both outdoor and indoor setting. And here, as we actually approached the underground car park, the localization was able to continue based on the vision-based localization method, although GPS becomes unavailable in this instance. And the key component of our technology is about information from 2D images, but still on embedded systems. Here we utilize a self-supervised learning approach to estimate depth for each pixel from just monocular camera images. We have again applied optimization methods such that such a model can deploy on low power embedded systems. When we compare with academic benchmarks, we're able to achieve top ranking accuracy on a public data set compared with other models that would require much more powerful GPUs. Here the demonstration, the warmer the color it is, it means the closer it is to the Eagle vehicle. We've also tested our model on our own data set, as well as customer data set. And here's the demonstration of the point clouds being generated from monocular depth estimation for each frame. And next, I would like to talk about some of our collaborations with customers and partners and how we deploy those embedded intelligence for applications. In particular, we've been working with Siemens on a digital twin solution for autonomous driving. And here the solution is mainly used for validation and verification. And we have worked with Siemens on providing our 3D reconstruction algorithms in order to demonstrate an autonomous emergency braking function as a starting point in a closed loop digital twin, where a vehicle has been simulated on a physics level, and that's able to range from the ECU to steering system, braking system, as well as the simulation comes from different sensors modes, including camera, radar, etc. We've also presented this work with Siemens Unarmed on a partnership that's announced at the CES start of this year, and where we provide the 3D reconstruction and detection algorithms that was running on the ARM-based architecture that's able to generate the critical depth information in real time that provides signals that triggers an autonomous emergency braking function. And this has been demonstrated as part of a digital cockpit demo. Through this collaboration, we've also written articles on how we together built this 3D perception systems that could have a significant benefit in terms of the memory and also the processing footprint that's required. Some of the other collaboration we've had, including for passenger and commercial vehicles for both actually the production program that's looking at testing and validating the technology itself, and also in the retrofit space, utilizing existing sensors that's on specifically commercial vehicles. And the benefit of the solution is it provides scalable and modular perception modules for the customers to able to choose and arrange their architecture. And here are some just demonstrations on the 2D and 3D perception demonstration on the urban roads running on embedded systems and also actually in different geographic locations. So in overall AI-based perception at the edge, what we believe that the trade-off continues and there's still additional opportunities with the technology itself. The biggest trade-off with running AI at the edge, I believe it's also about cost efficiency versus robust perception. Where we adopt a modular approach to autonomous driving, and with perception being a critical and fundamental step for autonomous driving. But this is not where it stops. In order to actually plan path reliably, you need perception to know where it is and act around both dynamic and static agents in the environment, but also about how you plan and according to the situations, as well as taking a human-centered approach to being able to actually gain trust from humans on board as well. It is also about the efficiency of each software component and the cost of each component for both sensors and compute. And all of this can affect the viability and feasibility of autonomous vehicles on the application that's able to apply the technology to. And about deep learning possibilities, inevitably, it has increased the computational complexity, which could actually render some of the applications cost prohibitive. But there's optimization that could be applied that's able to maintain the level of performance as a much more complex model, but it'll be able to really implement in a real-time setting through the optimization method. So going forward, we believe that robust perception at the edge can continue to unlock the next generation autonomous solutions, and we're truly honored to be part of this journey. And if you're interested in hearing more about deploying AI-based perception at the edge, feel free to reach out, and I'm happy to answer any questions. Thank you.